In the vast expanse of our solar system, there's a planet almost forgotten by American space exploration, Venus, Earth's closest neighbor and once hailed as its twin. Despite their similarities in size and composition, Venus has been left untouched by U.S. spacecraft for over 3 decades. The last time NASA sent a probe to orbit Venus was back in 1989, with the Magellan mission. And what Magellan uncovered was nothing short of astonishing. Magellan wasn't your typical flashy mission. It was cobbled together from leftover parts of other spacecraft, its radar borrowed from Voyager, its propulsion module from Mariner, and its star scanner from Galileo. Born from budget cuts and political deal-making, Magellan was a mission of necessity. But it exceeded all expectations. After a 15-month journey through space, it entered Venus's orbit in August of 1990. For 4 years, Magellan's synthetic aperture radar pierced through the planet's thick, shrouding clouds to map over 98% of its surface with incredible detail, down to about 300 feet per pixel. What it found completely transformed how scientists viewed Venus. The surface was a bizarre landscape of massive shield volcanoes dwarfing any on Earth, vast lava plains stretching for thousands of miles, and strange flat-topped pancake domes formed by thick lava flows. There were circular features called coronae, created by mantle upwellings that warped the crust from beneath. Overall, the planet's surface seemed surprisingly young geologically. With fewer than 1,000 impact craters across the entire globe, an incredibly low number compared to the millions on the Moon and hundreds of thousands on Mars, Venus must have undergone a dramatic resurfacing event in the last few 100 million years. Before Magellan, scientists assumed Venus was a dead world, geologically frozen without plate tectonics or water to lubricate the crust. But instead, Magellan found signs of recent, perhaps even ongoing volcanic activity. Then there were the tesserae, highland regions resembling continents, with complex folds and deformations. These could be ancient crustal remnants predating the global volcanic resurfacing. If so, they might hold clues to an earlier Venus, one with a drastically different climate, maybe even oceans of liquid water. Unfortunately, Magellan's radar couldn't reveal their composition, and since then, no mission has returned better data. Magellan's operational life ended in October 1994, when NASA deliberately sent it plunging into Venus's upper atmosphere, where it burned up. And then, for 30 years, the United States never sent another dedicated mission to Venus. The spotlight shifted to Mars. The reason goes back to a moment in August 1996, when a team of scientists announced they'd found possible microscopic fossils inside a Martian meteorite called ALH84001. This rock had been blasted off Mars millions of years ago by an asteroid impact, journeyed through space, and was recovered in Antarctica in 1984. The supposed fossils looked like tiny bacteria, sparking a media frenzy and fueling NASA's focus on Mars missions designed to hunt for signs of past or present life. Though later studies showed those structures could have formed through non-biological processes, the momentum had already swung decisively toward Mars. The red planet became the centerpiece of planetary exploration, with mission after mission launched by NASA and other space agencies: Mars Pathfinder and its Sojourner rover in 1997, Mars Global Surveyor also in 1997, and more recently, the Perseverance rover and Ingenuity helicopter in 2020. Europe's Mars Express, India's Magellan, and China's Tianwen-1 orbiter with its Zhurong rover all joined the quest. Meanwhile, Venus faded into the background. Part of this shift came down to practicality. Mars is easier to explore. Its thin atmosphere makes landing less deadly, surface temperatures are cold but manageable, and solar panels work efficiently. Rovers can operate for years, even decades. Communications are reliable, and electronics don't require extreme thermal shielding. Venus, on the other hand, is a nightmare. Its surface pressure is crushing, almost 100 times that of Earth, and temperatures soar above 450 degrees Celsius, hot enough to melt lead. The atmosphere is thick with corrosive sulfuric acid clouds. No lander has lasted more than a couple of hours before succumbing to the brutal conditions. Electronics fail quickly, solar panels are useless. From a technical standpoint, Mars is the obvious choice. But science isn't just about what's easiest, it's about the biggest questions. And Venus is a planet full of mysteries that could unlock critical insights into planetary habitability. Why is Venus such a hellish wasteland today, when it may have once been a potentially habitable world? The evidence lies in the atmosphere, particularly in the ratio of heavy water to regular water. Heavy water contains deuterium, a heavier isotope of hydrogen with an extra neutron. Because deuterium is heavier, it's less likely to escape into space. Venus's atmosphere contains about 150 times more heavy water than Earth's, suggesting that the planet once held far more water, possibly enough to cover its entire surface in oceans. If Venus once had oceans, it would have needed a climate capable of sustaining liquid water, temperatures between 0 and 100 degrees Celsius, an atmosphere not dominated by carbon dioxide, and clouds not made of sulfuric acid. In other words, Venus might have been Earth-like. So, what went wrong? The answer likely lies in a phenomenon called the runaway greenhouse effect. Venus receives more sunlight simply because it's closer to the Sun, but early in the solar system's history, the Sun was about 30% dimmer than today. This means early Venus could have had temperatures similar to Earth's. As the Sun brightened, Venus warmed, causing water to evaporate into the atmosphere. Water vapor traps heat, which led to even more evaporation, a vicious cycle of warming and vapor buildup. Eventually, all the water ended up in the atmosphere as a dense layer of steam, trapping solar energy. Sunlight's ultraviolet rays then broke apart water molecules into hydrogen and oxygen. The light hydrogen escaped into space, while the oxygen reacted with surface rocks or atmospheric chemicals. Over hundreds of millions of years, this process stripped Venus of its water, leaving behind a dry, scorched world. At the same time, carbon dioxide accumulated because, unlike Earth, Venus lacks liquid water and plate tectonics to remove it. On Earth, rainwater combines with carbon dioxide to form weak acids that weather rocks, cycling carbon into the mantle. Without water, Venus's carbon dioxide just piled up, creating an atmosphere that's 96% carbon dioxide and heating the surface to more than 450 degrees Celsius. While this scenario is widely accepted, many questions remain. When did the runaway greenhouse effect start? Did Venus remain hospitable for billions of years before tipping into hellish conditions? Or was it never truly Earth-like? The answers matter because they shape how scientists interpret habitability across the galaxy. Thousands of exoplanets orbit other stars, many similar in size to Earth or Venus, and many lying in the so-called habitable zone, where conditions might allow liquid water. But without direct observations of their surfaces, it's impossible to know whether these worlds resemble Earth or Venus. What separates a paradise from a furnace? Without understanding Venus's history, we cannot answer that. Then came a surprising twist in 2020. An international team using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile announced the detection of phosphine gas in Venus's clouds. Phosphine is remarkable because on Earth it's produced almost exclusively by anaerobic microbes, organisms thriving without oxygen, living in environments like the guts of animals. There are no known non-biological processes on Earth that generate phosphine in significant amounts. So, finding it on Venus raised a tantalizing question: could life exist in the clouds? At first glance, the idea sounds crazy. Venus's surface is a hellscape, but about 50 kilometers above, conditions are surprisingly Earth-like. The pressure matches that at sea level, temperatures hover between 20 and 30 degrees Celsius, and liquid droplets exist in the clouds, though mixed with concentrated sulfuric acid. Some scientists speculate that microbes might live suspended in these droplets, using sulfur chemistry for energy, carried by winds across the planet. However, extraordinary claims require extraordinary proof, and the initial phosphine detection quickly came under fire. Other researchers re-examined the data and found flaws, processing errors, statistical uncertainties, and possible contamination from sulfur dioxide, a gas with a similar spectral fingerprint. Some concluded there was no phosphine at all. Others suggested the amounts were far smaller than first claimed. Subsequent observations with NASA's SOFIA Airborne Observatory, the Infrared Telescope Facility in Hawaii, and data from Europe's Venus Express orbiter showed no signs of phosphine. The scientific community became divided. Some stood by the phosphine detection, others dismissed it as an error. Then, in 2024, fresh observations from the James Clerk Maxwell Telescope once again detected phosphine, this time with improved data quality and analysis. More intriguing was the hint of another gas, ammonia. Like phosphine, ammonia shouldn't survive long in Venus's harsh, oxidizing atmosphere. It's also primarily produced by life on Earth. What makes ammonia particularly fascinating is its chemical role. When mixed with sulfuric acid, ammonia acts as a buffer, reducing acidity. If microbes were producing ammonia in Venus's clouds, they might be creating tiny pockets of less acidic environments, microhabitats where life could survive. While this doesn't prove life exists on Venus, it points to something unusual taking place in the clouds, something current atmospheric models fail to explain. Scientists have proposed various hypotheses, but the story of Venus remains one of the biggest puzzles in planetary science. It's a world that challenges assumptions, forces a rethink of what it means to be habitable, and holds the key to understanding not just our nearest neighbor, but the countless Earth-like worlds scattered across the cosmos. Volcanic activity releasing phosphites, those mineral compounds containing phosphorus in a reduced state, lightning-driven chemical reactions, strange photochemical processes on dust particles, and other exotic atmospheric phenomena have all been proposed to explain the mysterious presence of phosphine in Venus's atmosphere. Yet none of these explanations fully add up. Volcanism on Venus would require massive amounts of unusual magma compositions, something that seems unlikely. Photochemical models fall short, unable to produce enough phosphine to match what's been detected. As for lightning, if it even occurs on Venus, it's incredibly rare and weak, not enough to drive the observed chemistry. The honest truth is, scientists just don't know. Our understanding of Venus's atmospheric chemistry is still incomplete, leaving open the possibility that these processes are entirely non-biological. But we can't confirm biological origins either, not without far more data. The answer lies in getting up close and personal with Venus, sending probes directly into the clouds to take real-time measurements of its chemistry and atmospheric dynamics. Unfortunately, humanity hasn't visited Venus in decades. We lack the missions, the technology, and the data needed to solve these mysteries. That is, until recently. In June of 2021, NASA stunned the planetary science world by selecting not one, but 2 missions to Venus under its Discovery program. The first, named Da Vinci Plus, which stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging Plus, will plunge through Venus's atmosphere all the way down to its surface. This probe will analyze the atmosphere in unprecedented detail, measuring noble gases, isotopes, and trace chemicals. As it descends through the dense clouds, its cameras will capture surface images sharper than ever before. Infrared spectrometers on board will identify minerals on the ground beneath the thick haze. One of Da Vinci Plus's primary goals is to pinpoint when Venus lost its water. By examining the ratios of various isotopes of noble gases, scientists can reconstruct Venus's thermal history, when it released gases from its interior, when its atmosphere began to escape into space, and whether it held onto oceans for billions of years or lost them early on. The mission will also investigate Alpha Regio, a rugged highland region with tesserae terrain that might harbor clues to a wetter past. If the rocks there contain minerals that only form in liquid water, that would be solid proof Venus once had oceans. Conversely, if the rocks are purely volcanic, it suggests a drier history. Da Vinci Plus will survive the descent for about 1 hour, before crashing onto the surface and losing contact. But in that single hour, it will collect more direct atmospheric data than we've gathered in the last 40 years combined. The second mission is Veritas, Venus Emissivity, Radio Science, in SAR, Topography, and Spectroscopy. Veritas is an orbiter equipped with a cutting-edge radar system far beyond what the Magellan mission used decades ago. It will map the entire planet in 3 dimensions at stunning resolution, down to about 30 feet per pixel. It will also use infrared spectroscopy to determine the composition of surface materials and study Venus's gravity field to peer inside the planet's interior structure. Veritas aims to uncover active volcanism, detect recent lava flows, and spot crustal deformations that hint at magma movements beneath the surface. It will study the tesserae in far greater detail than before, trying to figure out if these regions are sedimentary, volcanic, or something else entirely. The mission will tackle big questions Magellan left unanswered. How often does Venus erupt? Could it have plate tectonics? Or has it evolved through some other geological process? How is its internal heat distributed? When will it launch? Both Da Vinci Plus and Veritas are slated to take off in the early 2030s, with Da Vinci Plus going first, followed by Veritas a few years later. Europe is joining the effort as well. The European Space Agency has greenlit Envision, an orbiter designed to complement Veritas. Envision will carry radar instruments for high-resolution surface mapping and spectrometers to analyze the atmosphere and surface in detail. Instead of global coverage, it will focus on targeted areas of interest, providing detailed regional surveys. It will also carry radio science experiments to measure Venus's gravity field precisely, revealing clues about the planet's internal layers, whether it has a liquid core, a solid mantle, or Earth-like distinct layers. With these three missions from two space agencies arriving at Venus in close succession, a new era of exploration is underway. After nearly 30 years in the shadows, Venus has reclaimed its spotlight. The scientific community has realized what was missed during decades of Mars obsession. But these aren't the only missions in the pipeline. Russia's space agency has proposed Venera-D, a combined orbiter and lander mission targeting the 2030s, while India plans to launch its own Venus orbiter as early as 2028. Even private companies are exploring atmospheric missions using balloons or floating platforms. Exploring Venus isn't easy. The planet's surface conditions are among the most hostile in the solar system. Surface temperatures soar beyond 450 degrees Celsius, hot enough to melt lead. The atmospheric pressure is crushing, about 92 times what we experience on Earth. The thick atmosphere is saturated with corrosive sulfuric acid clouds that can rapidly degrade most materials. Carbon dioxide under such intense pressure behaves like a supercritical fluid, either quite a gas nor a liquid, which complicates heat management. Traditional electronics fail within minutes. Silicon chips can't handle temperatures above 150 degrees Celsius, solder melts, batteries die, mechanical parts seize, and lenses fog or crack. Back in the Soviet era, the Venera landers tackled these challenges head-on with brute force engineering, thick-pressure vessels, massive thermal insulation, and blocks of lithium nitride salt to absorb heat through phase changes. They relied on simple mechanical instruments, designed to operate just long enough to send back data before succumbing to the harsh conditions. Even so, the longest survival time on Venus's surface was about 2 hours, with most landers failing much sooner. Modern technology offers new hope. Silicon carbide semiconductors can operate at temperatures above 500 degrees Celsius and are already used in aerospace applications requiring extreme heat resistance. NASA's Glenn Research Center has developed silicon carbide integrated circuits that have run for over 500 hours in ovens set at 500 degrees Celsius. Some chips lasted for 60 days in simulated Venus surface conditions, 100 times longer than traditional electronics. This breakthrough opens the door to surface missions that could last weeks or even months, rather than just minutes. However, silicon carbide electronics are still basic compared to today's silicon chips. They're roughly as powerful as 1970s-era computers, limiting the complexity of instruments and rovers that can be built with this technology. So surface missions will remain focused on targeted investigations rather than extensive exploration, carrying simple tools like temperature sensors and drills to sample surface materials. Atmospheric missions face a different set of challenges. The clouds are less hostile than the surface, with more manageable temperatures and pressures. But the atmosphere's dynamics make navigation tricky. Venus rotates very slowly, one full rotation every 243 Earth days, but its atmosphere races around the planet at speeds up to 225 miles per hour, faster than the most powerful hurricanes on Earth. Any probe or balloon would circle the planet in just 4 days, swept along by the winds. Steering is nearly impossible. Missions must go where the winds carry them. That's not necessarily a deal-breaker. Instead of rovers driving to specific spots, floating platforms can drift with the atmosphere, descending wherever the winds take them and focusing on atmospheric measurements and remote sensing. NASA has studied concepts for solar-powered aircraft that could fly indefinitely in Venus's upper atmosphere, cruising at altitudes of about 30 to 40 miles, where conditions are relatively mild. These aircraft would use solar panels on both their tops and bottoms, taking advantage of Venus's bright reflected light from below, nearly as intense as sunlight from above. Such an aircraft would ride the fast winds, circling the planet every few days, carrying instruments to study atmospheric chemistry, cloud structures, and even surface features using radar and infrared imaging. It could also serve as a relay station, communicating with surface probes. While challenging, these missions are technically feasible and would provide long-term observations impossible from orbiters alone. The biggest obstacle remains cost. Missions to Venus demand custom engineering unlike anything required for Mars or other destinations. Mars rovers benefit from decades of proven designs and commercial electronics hardened against radiation. Venus missions need entirely new technology, which drives their price tag higher. This leads to a vicious cycle. Venus missions are expensive and rarely selected, so technology development stalls, keeping costs high and missions rare. Breaking that cycle requires sustained investment, and a series of missions that build on one another, developing standardized platforms and gradually improving components. This is exactly what happened with Mars. Early missions were risky and costly, with many failures. But over time, costs fell and success rates climbed until Mars exploration became routine. Venus could follow a similar path, if the scientific community commits to returning. The decision to send Da Vinci Plus, Veritas, and Envision signals that commitment. Whether this marks a brief surge of interest, or the start of sustained exploration remains to be seen. Yet the deepest reason to study Venus isn't just about Venus itself, it's about Earth and the thousands of rocky exoplanets we're discovering around distant stars. Earth and Venus are remarkably similar in size. Venus's diameter is about 95% that of Earth's, its mass roughly 82%, and their densities nearly identical. Both formed from the same primordial solar nebula around the same time. And yet, their destinies diverge dramatically. Earth became a vibrant biosphere with oceans full of life, continents carpeted in forests, and an atmosphere that breathes and evolves. Venus transformed into a hellish world with crushing pressure, superheated surface temperatures, and a thick carbon dioxide atmosphere. Understanding why two such similar planets ended up so differently is one of planetary science's most crucial questions. It reveals the factors that determine habitability, what conditions allow life to flourish, and what pushes a world past the point of no return. This knowledge is vital as astronomers discover thousands of exoplanets, many rocky and orbiting in their stars' habitable zones. But with limited data, size, mass, orbit, and sometimes atmospheric clues, determining if these worlds are truly habitable or more like Venus remains a challenge. Venus acts as a benchmark, showing the warning signs when greenhouse warming spins out of control, oceans evaporate, and atmospheres turn into dense carbon dioxide blankets. By studying Venus, scientists gain the tools to interpret exoplanet observations better, distinguishing Earth-like worlds from scorched wastelands. If Venus-like planets are common, true Earth analogues might be rare gems. If the threshold for runaway greenhouse conditions is narrow, habitable worlds become precious outliers. Or if Venus's fate hinged on subtle, still unknown factors, predicting habitability will require far more detailed data. Venus also holds lessons for Earth's future. Climate models predict that in about 1 billion years, as the sun gradually brightens, Earth will cross a tipping point leading to a runaway greenhouse effect. Oceans will evaporate, water vapor will trap more heat, and hydrogen will escape to space, transforming our planet into a Venus-like state. This fate is inevitable, but the timeline depends on details scientists are still unraveling: how quickly water escapes, feedback mechanisms, and the temperature thresholds for irreversible change. Venus has already undergone this transition. Studying it offers insights into how fast it occurs, what the end state looks like, and whether there could be intermediate stages where life might survive and refuges before the final collapse. This isn't just academic curiosity. Understanding Earth's long-term trajectory helps humanity appreciate the fragile window of habitability it currently occupies and frames the context for shorter-term climate changes. Importantly, human-driven global warming, while serious, will not turn Earth into Venus anytime soon. The two processes operate on vastly different scales and timelines. Venus stands as both a warning and a key to unlocking the secrets of planetary evolution, habitability, and the future of our own world. The upcoming missions promise to transform our understanding of this enigmatic neighbor, and in doing so, shed light on the broader cosmic question of where life can thrive. The runaway greenhouse effect on Venus is not something that happens just because of human carbon dioxide emissions here on Earth. It requires a very specific set of conditions, ones that we simply can't replicate with our current pollution. But by studying how these greenhouse effects spiral out of control and reinforce themselves, scientists gain crucial insights into how planetary climates respond to disturbances. Venus shows us the extreme end of the spectrum: what happens when a planet's atmosphere traps heat relentlessly. Meanwhile, Earth represents balance and stability. Together, these two planets draw the line between what makes a rocky world livable and what turns it into a blazing inferno. To truly grasp these lessons, we have to go there. Not just observe from afar with telescopes, which have their limits, but send spacecraft directly to Venus. We need to analyze its atmosphere in real time, study the surface up close, watch volcanic activity as it happens, and track its atmospheric shifts over months and years. That's why upcoming missions like Da Vinci Plus, Veritas, and Envision are so critical. These aren't just routine trips to another planet. They are key investigations into the very nature of planetary evolution, habitability, and how Earth fits into the cosmic puzzle. For 3 decades, Venus was largely ignored. Mars took center stage because it's easier to explore, with manageable engineering challenges and the tantalizing possibility of past or present life. But Venus, our opposite twin, was left in the shadows. That choice came at a cost. We lost 30 years when we could have been gathering data, advancing our understanding, and preparing for long-term exploration. The questions Venus raises are profound and simply can't be ignored. When did Venus lose its oceans? Was it habitable for billions of years, or did it turn hostile soon after it formed? Are the strange highland regions, called tesserae, ancient continents or something else? Are volcanoes still active today? What's causing the mysterious phosphine and ammonia detected in its atmosphere? All these mysteries could have been unraveled with missions that were never launched. But now, the tide is turning. The upcoming missions will arrive in the 2030s, ushering in a new era of Venus exploration. They'll map the surface with unprecedented detail, measure atmospheric chemistry with precision never before achieved, investigate the planet's interior, and search for signs of active volcanism. Envision, in particular, will zero in on specific features with high-resolution instruments, helping to decode the planet's complex geology. Still, Venus will remain enigmatic. Every mission so far has uncovered more puzzles than answers. Its atmosphere behaves differently than models predict, the surface appears much younger than expected, and the chemistry is full of surprises. Venus is chaotic and hostile, a world that refuses to be neatly categorized. Mars, by contrast, feels more straightforward, its story etched clearly in rocks and dust. But science isn't about choosing the easy path. It's about tackling the toughest questions, even when the answers are elusive. Venus holds the key to understanding how Earth-like planets evolve, what determines their habitability, and how common worlds like ours might be throughout the universe. It's time to stop turning away. The planet still hangs in our sky, cloaked in thick clouds of sulfuric acid, holding secrets that could reshape our knowledge of planetary science and even the search for life beyond Earth. The Soviet landers gave us brief glimpses of the hostile surface decades ago. The Magellan spacecraft mapped its terrain, but left us wondering why the surface is so young. Atmospheric studies hinted at strange chemicals but couldn't pinpoint their sources. Every step forward has led to new mysteries. Da Vinci Plus will plunge through Venus's dense atmosphere, measuring its composition and snapping photos of the surface below. Veritas will orbit for years, monitoring volcanic activity and mapping every tesserae with fine detail. Envision will complement these efforts, filling in gaps and exploring key features with sharp instruments. Together, these missions aim to answer the big questions. When did Venus become the hellscape it is today? How fast did this transformation happen? Was there ever a window when life could have existed there? What forces shaped its surface? Could life even survive in the clouds? But even with all this, Venus won't give up all its secrets easily. No 3 missions could solve everything. The universe rarely offers simple answers. Progress comes from patience, careful measurement, and sustained exploration. For too long, humanity walked away from Venus. That was a mistake, but it's a mistake that can be fixed. The plan now is clear: return not because it's easy or trendy, but because understanding Venus means understanding Earth's past, present, and future. It means grasping what makes a planet truly habitable and recognizing the fragile balance that keeps our world a paradise in the vast emptiness of space. These missions will launch in the coming years and arrive in the 2030s, bringing a flood of new data from our long-neglected twin. Venus, the planet that transformed into a furnace, will finally tell its story. And through that story, it will teach us how to spot life elsewhere, how to preserve it here, and how precious our own blue planet really is. Venus waits, patient and eternal, veiled in its acidic clouds, ready to reveal the secrets that have puzzled scientists for generations. The time to go back is now.